Hi, this is Surface Plasmon Resonance for the Optics Lab of Fall 2024. In its simplest setup, this experiment consists of a glass prism, an extremely shallow metal conductor, a solution media of interest in a container, all placed on a rotary stage in a way where they're packed tightly together and they all share a common surface normal axis. A monochromatic laser light is then directed onto this common interface at some incident angle. Specifically, the beam will refract through the prism and then converge onto the surface of the metal. From there, energy from the beam will be transferred to the surface electrons on the metal sheet, which will then oscillate and generate a plasmon wave, which will propagate on the other side of the metal that's adjacent to the solution medium. The beam then reflects off the metal surface, transmits back through the prism into space, and then ideally into some detector. The localized photoelectric energy transfer leads then to a very dim spot in the reflected beam due to some of its energy being absorbed by the metal instead of fully reflected back. Properties of the third medium in which the plasmon wave will partially propagate through, such as its refractive index, will have great influence over how this plasmon wave is formed and how it will propagate. And of course, this will affect where in space this location of dimming will occur with respect to the rest of the reflected beam. This phenomenon is useful in interdisciplinary sciences, such as biology and chemistry, as it can instantaneously track in real time changes in a substance. There are some hardline conditions that must be met for this experiment to be successfully pulled off. The laser beam must be linearly polarized, parallel to the plane of incidence when making contact with the apparatus. The incident beam must also totally internally reflect inside the prism. This means that the incident angle should be below the critical angle that corresponds to the refractive indices of the third medium and the prism. The metal sheet should be on orders of magnitude of nanometers in thickness, and the light should be monochromatic as to account for and control dispersion relations of these materials. There does exist an analytical equation for calculating the approximate angle of the SPR phenomenon shown below. Theta resonance internal is the angular location of the SPR dimming, and 1 is the refractive index of the prism. Epsilon prime would be the corresponding permittivity of the metal conducting material that's used. Epsilon d is the permittivity of the solution, and lambda naught is the specific wavelength of the laser. Because permittivity is merely the square of a material's refractive index, it can be noted that the SPR dimming angle is generally proportional to the refractive index of the solution medium. For this set of materials, there exist dispersion relations, as in the refractive index of material varies with the wavelength of the light that interacts with it. This can be shown in the figure below the equation. In the case of the metal specifically, that refractive index is also a complex number, which is why the equation takes the square root of the permittivity, which takes the overall real magnitude of the refractive index. The components of this lab included a helium-neon monochromatic laser, a linear polarizer, a rotary stage with angular markings on it, semicircular glass prism, 5 nanometer silver sheet, a container for which the solution medium would be stored in, a syringe, water, salt, and sugar for swapping out the solutions and changing them, as well as some substitutions such as paper and a meter stick for measuring angles precisely without a detector.
Using the provided prism stand, the provided helium neon laser, and a P-type polarizer, we investigated SPR. Our setup was fairly simple. We just sent the laser straight through the P polarizer and aimed it at the center of the fluid cell on the prism apparatus. We chose this point because we reasoned that it would be the one place on the silver square on the back of the prism, once that part was assembled, that would never be out of range of the laser as long as it didn't have an angle of incidence greater than or equal to 90 degrees. In terms of how we calibrated the polarizer, we set it such that the output of the laser was minimized and then rotated 45 degrees from that so that we could get horizontal polarization out of the vertically polarized laser. In order to find the angle of incidence, we traced the path of the laser on paper using a screwdriver. We plotted 2 points from the incoming and the reflected beam and drew a line between the respective points. We then connected them in a right triangle where the hypotenuse was the reflected beam's path and the long side was the incoming beam's path, and used trigonometry, by basically measuring the side lengths, in order to find the angle in between those two lasers. We reasoned that the angle of incidence that was causing the SPR phenomenon, if it were at the center of the laser pattern we were seeing on paper, would be half of the angle in between the incoming and the reflected laser beams. For, respectively, the fluids air, water, 1% concentration sugar solution, and 5% concentration saline solution, we observed the minimal reflectance at angles of incidence of 10.675 degrees, 8.935 degrees, 6.472 degrees, and 10.5 degrees. Although this differed significantly from the calculated angles at which the minimal reflectance should be occurring, in the same order as above, at 42.9 degrees, 52.7 degrees, 52.723 degrees, and 53 degrees. Results didn't correlate very well with the theory, unfortunately. One likely explanation is that the seal between the silver square and the fluid cell was bad. The silver square was too small to cover the entirety of the fluid cell, and as a result, when pushing fluid through the cell, it often ended up leaking. This prevented us from getting a complete covering of liquid on the back of the silver square. We attempted to work around this by squirting some fluid onto the square directly, but clearly this didn't help. As a consequence of this, all 3 of the water-based fluids might have imperfect results. Analyzing the equation qualitatively suggests that as the refractive index of the fluid behind the silver square increases, so too should the angle at which you see the minimal reflectance. However, this was contradicted in our case for a number of reasons, but most important of which, air had the greatest angle at which we observed the phenomenon, despite having the lowest refractive index of all the fluids we tested. Air, water, 1% sugar, and 5% saline solutions, the errors were, respectively, 75%, 88.7%, 93%, and 80%. This indicated systemic problems in data collection. Skin oil contamination could have caused us to see patterns that weren't the minimal reflectance area we were looking for. It's also possible that the minimal reflectance area that we were actually looking for occurred past the critical point of the prism, beyond which it's very difficult to identify a point of low reflectance by eye, because the pattern gets much more complicated visually past 45 degrees on the prism scale. The solutions also didn't have entirely accurate concentrations because we were unable to measure the mass of the sugar and salt that we used. This could have caused some of the problems in the measurements for the sugar and the salt solutions, but obviously could not have affected either water or air. And as stated before, the fluid cell lacked a proper seal with the silver square, causing all of the fluids to be somewhat questionable.